Hello children, welcome back to the channel. Today, before starting our discussions on intensity of gravitational field and gravitational field, let's first solve the problems that I have given in my third video of this series. If you haven't seen those videos, the link of those videos will be given in the description below. You can always refer to them. Now, the problem that I had given was, first problem that I had given was that if radius of Earth decreased spontaneously by 2%, by how much will the acceleration due to gravity will change, or what percentage will the acceleration due to gravity will change. Okay, so to solve this, first let's call in the help of or the expression for acceleration due to gravity, which was gm by r squared, that is on the surface of the earth, right? So to solve this, what we have been given that how g changes has been given, how r changes has been given. Now when we say radius decreased by 2% or decreases by 2%, what it means is that the final radius is lesser than the initial radius by a percentage of 2. So if r was the initial radius and r dash is the final radius, then r dash minus r by r will be minus 0.02. In terms of percentage, it will be minus 2%. We need to remember that. Okay, final radius is smaller, so the r becomes smaller. The mass remains the same. Now if g is given by this, then to solve this, what we will do is that we want to find the variation of g with r. So there are different methods, but the simplest and easiest method is to call in the help of another concept of mathematics, that is of logarithm. That is to say, if we take logarithm of both the sides, we get logarithm of g must be equal to logarithm of gm by r squared. Now we know the property of logarithm, that if we have product, then say log AB is equal to log A plus log B, and log of C by D equal to log C minus log D. So we will make use of both of them and say the numerator part will be log of Gm minus log of r squared, okay, which will be log of g plus log of m minus again log of x squared equal x to the power n equal to n log x. Making use of this, we get 2 log r, okay, which means log of g will be given by this, logarithm of g will be given by this. Now if we differentiate both sides, what we will get? We will get dg by g will be equal to, if we differentiate a constant term, since g is a universal gravitational constant, if we differentiate that term, we know differentiation of a constant is 0. So log g being a constant, log g will be a constant, and so it will be 0. Plus, we say that mass doesn't change, mass of earth remains the same, which means m is also a constant, so log m will be a constant, and so differentiating this will give us 0, will be equal to minus 2 dr by r. Okay, so what we get is that dg by g equal to minus 2 dr by r. Okay, now if you come to this expression, what we have found is that r dash minus r. Now what is r dash? See, initially it was r, and finally what happens? R dash. R dash is equal to r plus say change of r, right? So we don't know whether it's positive or negative. We assume it's positive. Whether it's even if it's negative, it's not going to change anything. So if I substitute r dash by r plus dr, then what we will have, this equation will be dr by r, which we have found to be minus 0.02 as has been given. 2% is equal to minus fraction. If you convert it into fraction, it will be minus 0.02. And since there is a reduction of mass radius, so it will be minus. So if you substitute this value, what we will get? Minus 2 into 0.02. Okay. Sorry, minus 0.02. Which will mean that this will be equal to 0.04 plus 0.04, or if you express it in percentage, that will be 4%. So what we have seen is that r decreases by 2%, acceleration due to gravity will change by 4%. However, it's a positive term. The final value is positive, which means that acceleration due to gravity will increase. You will need to note this particular point, that if radius increases, keeping the mass constant, acceleration due to gravity will increase. In this case, by 4%. Now, for the second problem that we had discussed, or I had given, was that if a man can jump to a maximum height h of 1.5 meter on the surface of Earth. From the surface of Earth, he can jump up to 1.5 meter. How high he will be able to jump? That is height in a different planet. What will be the height up to which he will be able to jump if the density of the planet is 1/4 of that of the Earth? That is, rho p is rho Earth divided by 4 density of the planet, and radius of the planet is 1/3 of radius of Earth. So r of the planet is equal to r Earth divided by 3. We want to find h. Okay, so first of all, what we will do is that we will first find the acceleration due to gravity in the new planet with respect to the Earth. Acceleration due to gravity of Earth we already know. So what will be the acceleration due to gravity in the new planet? So in terms of planet's values, acceleration due to gravity in the planet will be g, mass of the planet, divided by radius of the planet squared. G is given by gm by r squared on the surface of the planet, which will be g 4/3 pi rho of the planet into radius of the planet cube. 4/3 pi r cube is the volume of the planet multiplied by the density of the planet, right? Divided by r p squared, which will be 4/3 pi g, these are constant, rho p, and these two will give us r of the planet. Right? Or what we can also do is that without substituting this, we can do, okay, now we have these two, and rho p and rp we can express in terms of Earth, right? So this will be equal to 4/3 pi into g, rho p will be rho Earth divided by 4 into rp will be r of Earth divided by 3. So this will be 1/12 4/3 pi r e rho e into g. Now, if you remember, also in my previous video, we already have found that this expression is equivalent to this expression. That is to say, this expression is going to give us the acceleration due to gravity on Earth's surface. Like this gives us the acceleration due to gravity on the planet's surface. So this will be 1/12 g e. Okay. So I hope you are clear till this. Now, since the man can jump up to a particular height, say this height, h earth. So when he reaches here, his potential energy will be, we know, m g of r into h e. Now in the new planet, when he jumps, he can attain the same maximum potential energy, right? So for the new planet, mass of the man will remain the same. Acceleration due to gravity of the planet will be different, and height to which he jumps will be different. But maximum potential energy that the person can attain on Earth's surface will have to be the same as the maximum potential energy he can attain in the new planet. This gives us an opportunity to find HP. So we simplify this and we get HP equal to acceleration due to gravity on Earth's surface divided by acceleration due to gravity on the planet's surface multiplied by height on Earth's surface. Now GP we already know is this. So if you substitute this value, we get GE divided by G on Earth divided by 12 into HE. That is 12 times HE. Now HE we already have 1.5. If we substitute the value and multiply, we get 18 meter. So a man who can jump up to a height of 1.5 meter from the Earth's surface can jump up to a height of 18 meter from the surface of a planet whose density is 1/4 that of the Earth and whose radius is 1/3 of that of the Earth. Alright. Now let's get into the today's topic of discussion, that is intensity of gravitational field. Now, before we try to understand the intensity of gravitational field, we need to understand what is a gravitational field or what is a force field. See, gravitation is a force, right? Force of gravitation, that's what we are discussing. Now, what do we mean by field or gravitational field or field of a particular object or particular mass? See, what happens is that we know that gravitational attraction of a body depends or varies or decreases as one by r square, where r is the distance of the point where we are calculating the gravitational force on an object by a given mass, right? So if I say we have a mass here, capital MC, then as we move away from this mass, the distance will increase. The distance from the point will increase, its influence or the force exerted by it will keep on decreasing in all directions, not only along the positive x, but in the three-dimensional space around it. As wherever we move, if we move away from the mass, the acceleration or the force will keep on decreasing, right? So around the mass, given mass, there will be a region of space where we can experience its gravitational pull. That region of space where we can measure or experience the gravitational pull of the given mass is known as the gravitational field of the mass. Okay, so for different masses, the gravitational fields will have different values, that is different strengths or intensities, and also it will have depending on the distance, it will also vary. So Earth's gravitational field is weaker compared with the gravitational field of the Sun, as we know, because Sun is much more massive compared with the Earth, and gravitational pull depends on the masses involved, right? So the Sun has a much bigger gravitational pull, and so its influence can be felt to farther away, and that is why the solar system, all the planets of the solar system are rotating around the Sun, whereas Earth's gravitational pull is much weaker. However, it's strong enough to keep the Moon in its orbit. So what we are trying to say is that the area around any mass, even this plane, has a gravitational field around it. However, it's not very strong, and that's why we do not experience its force on, say for example myself, will be much smaller, or conversely my gravitational pull on the plane will be much smaller compared with that of the Earth. That's why if I release the plane here, it will not get gravitated towards me, it will go gravitated towards the Earth, because my mass is negligible compared with the mass of the Earth. So whatever be the case, more massive the body, the gravitational attraction or the strength of the field will be more. So we define a term intensity or strength of a field of a mass or around a mass. How we define that? We define that as, let's say we have a mass placed here, say small m, which center to center distance is r. Then we know that force of gravitational attraction on it will be F equals to G capital M small m by small r squared. Right. Now, instead of putting a mass m, if I equate the mass, or we have this mass equal to unity or unit mass, that is 1 kg or 1 gram, depending on the scale you are taking, then what will happen? What will be the force on that particular mass? That is to say, if I take F and divide it by the mass, then we get Gm by r squared, which is, what we are doing is that by unitary method, F by m is force per unit mass. So this force per unit mass at that particular point is known as the intensity at that particular point. That is to say, this is equal to gravitational intensity E. So intensity of a gravitational field at a given point or at any point is given by the force experienced by a unit mass placed at that particular point. Clear? If we place a unit mass at a given point in the gravitational field of a given mass, this one, then at that point whatever force that unit mass will feel will be a measure of the intensity of the gravitational field. Now, since it's force per unit mass and we know that force is a vector, and divided by m will give us force per unit mass, so intensity itself is a vector quantity. It has a direction, and its direction we always know that gravitational pull is attractive always. So the mass, unit mass placed wherever, it will always be attracted towards the center of the given mass. So its direction will always be towards the given mass. Okay, now this expression, as you know, reminds you of something, that Gm by r square we know is that given by Gr. So acceleration due to gravity of that particular mass at a distance of smaller from itself will be given by this particular expression, which means that intensity of gravitational field at a given point is numerically equal to the acceleration due to gravity produced at that particular point by the given mass. Intensity is equal to acceleration due to gravity. However, intensity is given in a different unit compared with acceleration, though dimensionally they are both the same. For example, if I say, if I have to find the dimensional formula of E, it will simply be dimension of F by m, which is mlt square divided by m. So we are left with lt square, that is minus 2, L inverse T inverse 2, and unit of gravitational field will be given by Newton per kg, since it's force per unit mass, or it will be given by dyne per gram. Okay, however, you can clearly see that dimension of this intensity is same as the dimension of acceleration, and also Newton per kg, if you convert it, it is actually equivalent to meter per second square. However, to differentiate that, we are not talking about acceleration, we are talking about intensity, and intensity being defined as force per unit mass, so its unit will be given by Newton per kg or by dyne per second, and its dimension is of course m0 L1 T inverse 2. Okay. Next topic is gravitational potential energy. Now, what we mean by potential energy, we already know that potential energy is the energy possessed by a body by virtue of its position or its configuration. Right? Now, when we talk about gravitational potential energy, this is the energy associated with a body in a gravitational field by virtue of its position in the field. What we mean by that? Now let's say we have a massive object which has a mass of say capital M. It has a mass of M. So there will be a field around it, and at every point of the field there will be intensity. If you put a unit mass, what will happen? It will be accelerated towards the center, right? Or center in the sense center of the object or this massive body. Now, if I place a mass here, say somewhere, because of the acceleration pull, gravitational pull, this, even if you release it at zero speed, it will accelerate and it will accelerate and it will reach a certain velocity before it reaches the surface of it, which means it has acquired certain amount of kinetic energy before it reaches the body. Where did this kinetic energy come from? We know that energy cannot be created or destroyed. It can only be converted from one form to another, which means that this kinetic energy was achieved at the expense of some other kind of energy which was possessed by the body when it was placed at this particular point. And when we position an object at certain point in this field or near the object, so what we have seen is that as we define, potential energy is by virtue of position of the object. So in the gravitational field of this mass, by virtue of the object being placed at a given position, it will have certain energy, and that energy is, that potential energy is known as the gravitational potential energy. Okay, now where did this come from, energy come from? See, what we will assume, or we can say, look at it this way, that this object was initially somewhere, not in this field. What we did is that we brought that object from somewhere in the universe, maybe infinitely distant point, where the gravitational field of this object was, or this particular mass was zero, and we brought it from there and placed it in the field. So we had to do certain amount of work in bringing the object from infinity to this. That work done from the work energy theorem got converted and stored as the potential energy of the object. So the gravitational potential energy can alternately be defined as the work done in bringing the given mass, whose potential energy is measured, work done in bringing the given mass from infinite distance without any acceleration. Why do we say without any acceleration? Because if it had been given acceleration, it would have achieved certain amount of velocity, and that other than it would have attained certain amount of kinetic energy. We are not talking about kinetic energy. We said that the object had zero kinetic energy in the field. So we brought it very, very slowly so that the acceleration or the velocity of the object can be considered to be practically zero. So without acceleration, if you bring an object from infinity to a given point, say r, in the gravitational field at a distance of r, that is to say we bring it to this particular point P, which is at a distance of say r, small r, in the field. So whatever work we had to do to bring it from infinity to this particular point got stored as the potential energy, and that potential energy is the gravitational potential energy of the object. So we have two definitions of the gravitational potential energy. One is that potential energy of an object by virtue of its position in the gravitational field. The other one is that it's the work done, because work done got converted to potential energy. So work done in bringing it from infinity to that particular point in the field. Now we want to find the value of the gravitational potential energy at this particular point P. To do this, what we will say, using the second definition, the object was initially at infinity, and we brought it along this path from infinity. And let's say at any given point, it was at A, and the distance of the point A from the center of the given mass is x. Okay, so at point A, force of gravitational attraction will be capital G, capital M, and let's say the mass of the given object, the object whose potential energy we are trying to find is small m. So it will be gmm by x squared. At this particular point, the force of gravitational attraction. Right. Now, let's say we bring the object a little closer to the point towards the mass by a small distance b, to point B by a small distance of dx. So what we are assuming here is that when we bring it from A to B, the distance is so small that the force of gravitational attraction practically remains the same. So what will be the work done in bringing it from A to B? The work done in bringing the object from A to B, let's call this dW, will simply be the force this multiplied by dx. Excuse me. You see the force of attraction will always be towards the center, so it will be along the line only. So the angle between displacement and force will be 0, and that's why we are able to use this expression f dx. So we can rewrite this as g capital M small m by x squared dx. So what will be the total work done in bringing the object from infinity to point P, which is at a distance of r? That can be found by integrating this expression dW with the proper limit, which is, what is the proper limit? Initially the object was at infinity, finally it comes to r, and then we have gm m by x squared dx. Now we know that g, m and m, these three things are constants. So we bring this out of the sign of integration, and we have infinity to r 1 by x squared dx, or x to the power minus dx, which will give us g capital M small m 1 by x minus of 1 by x with the limit infinity to r. If we solve this, what we get? G m m minus 1 by r minus 1 by infinity. This term is 0, right? Which means total work done in bringing the object from infinity to point P, which is at a distance of smaller from the center of the given mass, is minus g m m by r. Now this work done gets stored as the potential energy. So the gravitational potential energy U at the given point P will be U equal to this. Okay. Now, once we have arrived at this particular expression, we will now, in my next video, that will be in the coming next tomorrow, we will discuss about the different properties and some special cases of gravitational potential energy in the next video. Okay.